Hello, good morning. Today we will be discussing the second topic, and this is quantum theory for evaluation of the transition rates, the Einstein coefficients, as well as allowed and forbidden levels. And these three subtopics are important to proceed for the better understanding of laser systems. I will start with in a reverse direction. First, I will discuss about the allowed and forbidden levels. Then I will discuss about the Einstein coefficients and then Einstein relations, and also then about the quantum theory for transition rates. So let's start with the first one. Uh, See, as far as the transition rules are concerned, we know from quantum theory that atoms absorb or emit photons when they jump between quantized states. Now, these quantized states uh, have different situations as because of their quantum numbers, and because of these quantum numbers, each will have different energies. And already we know about certain rules like Pauli exclusion principle, which states that no two electrons in the same atom can have identical values for all four of their quantum numbers. uh, all four of their quantum numbers, that means uh, the principal quantum number n, the secondary or the azimuthal or orbital quantum number l, the magnetic quantum number ml, and the spin quantum number ms. All these four quantum numbers cannot have the same identical values for two electrons at the same level. So with these rules, we find that there will be a number of restrictions on the atomic transitions which will take place from one orbital level or subcell level to another subcell level. Uh, if someone is more interested, uh, he or she can visit through this link also. And since we are just recalling the previous chapters, so we are going into slightly brief on these topics. Then let us go through the selection rules. The selection rules are identified here in terms of the change in the orbital number and change in the magnetic quantum number. So, for example, if the change in the orbital quantum number delta L is plus minus 1, if it is happening, then such a transition is allowed. If it is not happening, then such a transition is not highly improbable and we call it forbidden. Similarly, if a transition is happening, uh, uh, then another rule will be about the change in the magnetic quantum number, that is delta ml. And this delta ml, the magnetic quantum number, will have three directions x, y, z. So it will have three possible values, 0 or plus 1 or minus 1. So that means any transition has to follow first this rule and then this rule. But then these two are not sufficient. There is a third rule also, which we will come to that also. But in the meantime, just relate it with the electric dipole transition, because when we talk about the magnetic quantum number, automatically the electric dipole conditions is appreciated. So uh, this transition is like an electric dipole transition. Now the third selection rule is that the change in the spin quantum number should always be 0. Now you can understand, because in each orbital cell, if there are two electrons, one has a plus half spin, other has a minus half spin. So if transition is going to take place from one level to another level, then if the minus half is going to that level, then there are another let's say electrons there. Then if both have same spin, this will not happen. So all these conditions are to be fulfilled. Now, if you want more details, you can visit such links also. So this was about the basic selection rule for electronic transitions. Uh, Now we will move to another subtopic, and which will be related to population distribution uh, inside a cavity having two atomic levels. So let us consider first the Planck's distribution law, which we had discussed during last lectures on during our discussions on summary of black body radiation. Now, if you look here about on this whole diagram, the spectral distribution of this energy distribution, this density, that is spectral energy density rho v, depends upon the temperature T of the walls of the cavity. And Planck's law clearly explains this. And you can see here that the at which uh, the uh, peak at which the maximum energy spectral energy density occurs is at 18 terahertz, and this is the situation for thermal equilibrium at T equal to 300 Kelvin, and the spectral energy density at that particular frequency is so much, 2.6 into 10 to the power minus 19 joules per meter cube per hertz. Now uh, this is as far as the spectral energy density is concerned, and through this you can always calculate also that what will be the value of energy and how it will be dependent once the temperature equilibrium is known. So these are just some small calculations. I will be more interested into knowing about the population distribution, but this discussion was important to move forward. So now let us assume that in this cavity there are we are considering two energy levels. One is identified as first energy level 1, and the other is identified as second energy level. So the population distribution under thermal equilibrium at the, let's say at this temperature, will be given by n2 upon n1. That means population density at level 2 divided by population density at level 1 is equal to exponential minus e2 upon e1. That means energy at the level 2 and minus energy at the level 1 divided by kT. So this population ratio n2 upon n1 is a function of the difference of energy level between the two levels, right? And this we can easily correlate it with the Bohr's model, which gives you a value of h nu 0, because you can correlate it with E equal to h nu, so equal to E2 minus E1. And why we give as the nu 0? Because we are trying to identify a transition frequency with that energy gap which will be needed for an electron to transit from atomic level 1 to atomic level 2. Now, if we follow this, then our population ratio n2 upon n1 becomes e to the power minus h nu 0 upon kt. So this is the population distribution ratio as per Boltzmann statistics. Now we are in a position to introduce the Einstein coefficients. So let's move to Einstein coefficients. Now Einstein discussed three major uh, components of his coefficients. First is about the spontaneous emission. So we'll discuss it here. See, as you can see in this figure, the two atomic levels n1 and two atomic levels are given, 1 and 2, with the energy levels E2 and E1, and with population densities N1 and N2. Now, if emission has to take place, spontaneous emission has to take place, that means the atomic transition has to take place from the higher energy level 2 to the lower energy level 1 spontaneously. That spontaneously means there is no incident radiation available. Nobody is causing a radiation to occur. The radiation is happening on its own and at any time. Since it is happening at any time, that means whatever radiation will occur will be coherent and it will occur in all spatial directions. Now, once the emission is taking place because of the transition from N2, so there is a change in the number of population, change in population at N2. So this population change is defined as dN2 equal to minus A21 N2 dt. Now, this is for a particular period of time, right? So this small change in N2 is proportional to N2 dt and is equal to minus A21 N2 dt, where we consider A21 as the Einstein coefficient of spontaneous emission. Now the population of the upper level, level 2, decays exponentially, and this we can define as N2 at time t is equal to N20. That means before the start of spontaneous emission, whatever population density was there, N2 into exponential minus A21 into t, and this is further defined as N20 e to the power minus t upon tau sp. Now this tau sp is a spontaneous lifetime. So this explains that since there is no incoming radiation or stimulating radiation occurring, so the atoms transiting from level N2 to level N1 will be transiting as per their spontaneous lifetime. They will be doing it on their own. So, and you can see here that this spontaneous lifetime is reciprocal of the Einstein coefficients. It indicates another factor, that if the spontaneous lifetime is very high, the spontaneous emission coefficient, Einstein coefficient, will be very less. Right? Now this was about the spontaneous emission and about Einstein's coefficient of spontaneous emission. Similarly, we will talk about the absorption. The photons of a light field can be absorbed by the atoms at level 1, and then since they have absorbed the radiation, so they will jump to the level 2, and this transition from 1 to 2 will occur with some change in the population at N1. Now, like we did it here in case of spontaneous emission, we develop a relation of change in population at N1, that is dN1 equal to minus B12, transition from 1 to 2, rho nu 0. Because why? Because rho nu 0 is the incoming radiation at a transition frequency nu 0. This absorption is taking place because of this incoming radiation, spectral radiation, uh, spectral energy density radiation. So dN1 equal to minus B12 rho nu 0 N1 dt. Now B12 is emission Einstein coefficient of absorption, right? and rho nu 0 is the spectral energy density of incoming radiation. Now this absorption is only possible in the presence of the incoming radiation. So we have to call it as a stimulated absorption, unlike the spontaneous process. In spontaneous process, no incoming radiation was there. The atom was transiting from 2 to 1 on its own and depending upon its spontaneous lifetime. In case of absorption, it was doing it because of the incoming radiation, so it is a stimulated process. Now the third Einstein coefficient is about stimulated emission, and this stimulated emission, since it is talking about the emission, that means it is talking about the transition from 2 to 1, like in case of this spontaneous emission. The only difference is that unlike spontaneous emission, this is a case of stimulated emission. But again, since it is happening from the level 2, so the change in the population at N2 dN2, like we develop the relation here, or we develop the relation here, to equal to minus B21. Now B21 is Einstein's coefficient of stimulated emission, right? And this is now dependent upon rho nu 0. That means it this stimulated emission was possible because an incoming radiation having a spectral energy density of rho nu 0 caused such emission to take place from N2. So, and this radiation, because it is stimulated, so it will be similar in characteristics of the incoming radiation, uh, rho nu 0. So as you can see, it is written also, the radiation created by stimulated emission has the same frequency, direction, polarization and phase as the stimulating radiation. So now we know about the three Einstein coefficients. Now we have to develop the relation between the three Einstein coefficients. So let's start. uh, let's take the first case, and before doing that, we have to develop a relation of transition rate. So uh, the rate of change of the population n1, the rate of change of population n1, that is transition rate from the level n1 due to absorption. Transition rate, that means dn1 upon dt is equal to so much. This you can easily go back and see from the previous equation. So this you can all easily arrive at, is given by this value. Now similarly, uh, if we are to develop the transition rate for uh, for the stimulated emission from N2, that is the rate of change of population N2 due to stimulated emission. Again you go back to your previous equation, dn2, so dn2 upon dt becomes this much. So we have developed the relation for transition rates for absorption, we have developed the transition rates for stimulated emission, and similarly we are developing the relation for transition rate for spontaneous emission. These are developed from the previous relations. So all three relations are now developed. Now let us look at the equilibrium condition case. See, the absorption was happening from 1 to 2. That means atoms were transiting from one level to two level. So under thermal equilibrium condition, this absorption rate will be equal to the sum of the two emission rates. The first emission rate because of the spontaneous emission, so that is this one, right? And the second rate will be because of the stimulated emission, that is this one. So under thermal equilibrium, that means nobody is causing any extra effort. A temperature is there, an incoming radiation may take place or may be induced, but even then some spontaneous will always occur, that we have already seen, because uh, the the spontaneous lifetime factor is there for that to happen. So all the three phenomena are taking place and they are in this equilibrium. So if we put these values, then we get this relation, and from this relation you can easily derive the value of rho nu 0, which is this one. Now if you look at this value, and if you go back to the value of Planck's distribution law that was in the first slide, then, and if you compare this, then you will find that B21 equal to B12 and A21 equal to so much, right? I will just go back to show you this relation. Uh, uh, you can see here, yeah, this relation, right? And if you compare this relation with this relation, then you can equate these factors. Now this is the Einstein relations. So we have developed the Einstein relation. It's very simple, but we have ignored some factors, and the factors are: we have not considered the degeneracy of the atomic state so far, and also we have not yet considered the medium of the transitions. If the atomic transitions are taking place in a medium having some refractive index value, then the things will change. So let us come to some special conditions, and this is this. See, if there is a degeneracy of states, then what we will do is that we will give a statistical weight to level 2, that is G2, and a statistical weight to level 1, G1, or you can call it G1 as the degree of degeneracy of level 1 and G2 as the degree of degeneracy of level 2. And under such situation, the population ratio N2 upon N1 will become G2 upon G1, and this value. Uh, Under a case of non-degenerate situation, G2 will become equal to G1, and then you will go back to the previous relation. So this is clearly explained here. And under the case of degeneracy, B12 will become equal to G2 upon G1 into B21. And in case of non-degeneracy, B12 will be equal to B21. So, and this equation we have already seen uh, in the previous case, sorry, in the previous case, this one. So this is again rewritten here. So that means in the degeneracy case, the Einstein equations will be defined like this one, right? Now let us assume another condition, and that condition is that if the atomic transitions are taking place in a medium of refractive index n, then what will happen? Then your speed of light in vacuum will be replaced by uh, or it will be modified because of the refractive index value. So under such situation, your this equation 6.22 becomes equal to this value. As you can see here, the denominator c is replaced by c by n, right? And since we are more interested into knowing the B21 value, because we want stimulated radiation to be explicitly defined, so this equation is converted into B21 equal to so much. So this is the Einstein relations for a refractive index medium. But otherwise, you will be happy to use your relation at this level also. So depending upon case to case. Now, as you can see here, there are 2-3 critical observations which we'll try to discuss now. See, first is uh, you can see from this equation that B21 is inversely proportional to this cube of frequency. And what does it mean? That as we increase the frequency, the stimulated emission will go on reducing. That means lasing action will take place in a difficulty, and that is why at higher frequency, at ultraviolet or at X-rays, the laser action is difficult to achieve, or the efficiency will be very low, right? And that is why you get a lot of efficiency at higher wavelengths or lower frequencies. That is one observation. Second is that if you see the relation between A21 and B21, that means spontaneous emission and stimulated emission. You have to do a trade-off between the two. You cannot reduce A21, although A21, that is spontaneous emission, is a non-desired, but you cannot reduce it to zero, but you can try to minimize it, and this you can observe from the above table. As you can see here, uh, the spontaneous lifetime in helium neon laser is 100 nanosecond. That means it is very small. So for a small uh, uh, spontaneous lifetime, the A21, that is spontaneous emission coefficient of Einstein, is will be higher. And so if since it will be higher, that means the spontaneous emission will be much higher, and uh, so the lambda will be much less, and refractive index is here in case 1. Right, now here you can see the A21 is very high. Of course B21 is high, so this is a reasonable condition for me that even though A21 is high, B21 is also high. Now if the spontaneous lifetime is 5 seconds, then you can see here for a CO2 laser the wavelength is on a very high side, and here the spontaneous emission is very less. Although the B21, the stimulated emission is also less uh, than in case of helium neon, but the efficiency of CO2 laser will be very high because A21 is very less. So similarly, you can see the observations here, and try to derive a picture of how the spontaneous lifetime plays a role in the value of A21 and in the value of B21. So these are the observations, and all these relations were taken from a good text book, which I am using for reference also. And this is written by Carl F. Egg from Springer, and this I have been using it for last I think 5 years or 6 years. So anyway, uh, thank you so much for this course, for this chapter. So thank you.